Developments. Developments are surface area that would be occupied if an object were unfolded and laid flat. If you take a hollow painting cylinder and roll it through one revolution while wet, the outline made would be the development of a cylinder. In metalwork, sheets are cut and bent to form varying parts, but it must be precisely cut. Therefore, developments are used to determine where to cut and bend the material. An important consideration is also to make efficient use of the sheet to minimize wastage. So we'll be focusing on prisms and cylinders, pyramids and cones, and some examples of problems in simple development, slice objects, and intersecting solids. So the types of development. There's a parallel line development, where the lines of development stay parallel to the object itself. Radial line, where they come up to meet the peak of the object. A triangulation development could also be considered a radial line development and an approximate development. So a slice object. In the corner here we see a slice cylinder. So in the plan you divide into 12 equal parts, and then you the base of the cylinder using 2 pi r, you find the length to roll it out. And then you transfer these lengths along the cut base to each of the divisions along the base. So the circumference divided into 12, and the plan has the same 12 divisions, and you transfer each one to form the development of the cylinder. The method is similar for a cone, except the 12 divisions are carried at a right angle across and then in a circular manner to meet the equivalent division. Intersecting solids. So the way we do intersecting solids is that we do it in 2 parts. We have A and B. So A here is the base of it, which is 4 equal or square with 4 equal sides, and then each forming 4 rectangles. But where we have the intersecting part, we have the curve of intersection on the 2 ends. The same thing applies to B. You'd have the end, which is a hexagon, 6 equal sides, and then the 6 rectangles. And the top of it is the curve of intersection. Some developments require the true length to accurately create the development. True lengths are at right angles or parallel to orthographic projection lines. The edges of a cylinder are all parallel to their projection lines, while a cone only the edges are parallel. So if we look at the cylinder again, all the lines are all of them are parallel to the orthogonal lines. So these are orthogonal lines. So you can see that all of them are parallel when laid out. However, if you look at a cone here, all of the lines come up to meet a peak. So that the only line that is perpendicular or parallel to orthogonal lines would be 1 to 7. So the line on the edge of the cylinder is our true length, while all the others on the inside, they have to be transferred or carried straight across to the edge of it and then rotated in a circular motion to the equivalent division on the plan. So you must use a true length when you're dealing with cones. Any line that is not parallel or perpendicular to the orthogonal lines, you need to find the true length. Where cylinders are truncated, use the cross-section to determine the width of development. In the example, you will know that the circular end versus the elliptical cross-section. Development width is based on the arc distance of the ellipse or the approximate length of each arc. So this end has a circular cross-section here. The center cross-section, however, is an ellipse, as you can see on the base here. And then the development, the width. So we use the width of each individual piece to find the total length of the development. So you can see A, B, and C is based on the approximately length of each of the arc distances. And then you match the divisions as you go across to create the entire development. There are two approaches to the alpha form. You could use the apex as a radius and draw the arc equal to the circumference of the base, or you could apply a formula where r is the radius of the base cone, the big R is the slanted distance from the peak to the edge of the base, and then you multiply by 360. So in this example, 50 is the radius of the base here, 106 is the slant distance, then you multiply by 360, you get 169 points on, but we are approximately 170 degrees. So you rotate this side here 170, and you have the angle that contains the development. Again, you divide it into 12, and then you match up the equal divisions to each of the lines.